Welcome everyone to the SQL Server Performance Tuning two-step webinar. I'm Kostas Apopoulos, the Chief Field Technology Officer for Pavilion Data, and we're the sponsor of this webinar today. And we're excited to be joined by a couple very senior technologists in the VMware and Microsoft space. So as we look through this as the sponsor of this, again, I'm Kostas Apopoulos, Chief Field Technology Officer and a long storage industry veteran. You know, as the sponsor of this webinar, we're really going to focus on what Pavilion can do as a byproduct of all the work and efforts that SQL Server and VMware have done to unleash the power of Windows and SQL Server and VMware as a result of a very high performance storage subsystem with ultra low latency, whether that's small or large block size, whether it's read or write workload, whether it's bare metal Windows with SQL Server or some incredibly impressive performance running Windows inside of VMware with SQL Server. And whether that's leveraging a file protocol like an NFS or an NVMe over Fabric Rocky. So we're excited about the opportunity to introduce a couple of the key players for today's webinar. David Klee, the founder of Heraflux Technology and Sequilibrium Education, a self-proclaimed geek, consultant, and a performance tuner as enterprise DBA and infrastructure architect. As my experience, David is very, very strong in the SQL Server space, and we're excited about hearing what he has to say. We're also joined by Oleg Ulyanov, a senior cloud architect for VMware and a performance engineer, hybrid cloud, security and compliance, networking and storage, a very strong veteran in this space as well. And with that, I'm going to turn it over to David and Oleg. So David, over to you.
Awesome. Well, thank you, everybody. My name is David Klee. We are going to have a lot of fun today. Of course, I'm a nerd. You probably already picked up on that. We're going to talk about performance tuning from a database perspective and how it relates to everything underneath. We're going to talk about the best practices approach and then workload tuning on top of that. So by doing this, we're going to go through the physical layers of the infrastructure stack. We're going to hit the VMware hypervisor. We're going to hit the VM architecture itself, and then some operating system tuning tips, and then the SQL Server instance, and then some tips and tricks about workload tuning. And then we're going to open it up to Q&A. So to get started, performance tuning is as much of an art as it is a science, unless you make it a strictly objective science. Most people treat it as a back and forth act, where you tune, you monitor for changes and see how the system state responds, and then you go tune some more and you go back and forth. It doesn't always work like that. We can't just make changes for change's sake and expect things to just work better, because sometimes they don't. These things are multifaceted animals. They are living, breathing creatures. And I love quoting a friend of mine named Kellen: the clothes that fit your child when they were 2 don't fit your child when they were 10. These things not only take TLC to keep them running healthy, but it requires tuning over time. So the bottom line with all of this stuff, every infrastructure stack has got tons of layers. You've got the application workload placing, any number of different operational parameters on a database engine. You've got virtualization, the physical hardware on top of it. You've got the operating system and all the nuances that come with that. You've got the database instance, and then the database itself, and it's designed with how the tables are architected, the queries that go into it. And quite literally, every single change you make up and down the stack directly impacts all of this stuff. You have to tune each one to reduce all the bottlenecks. The hard part here, there's not an easy button for this. I really wish there was. It would make all of our lives just so much easier. So what do we need to do? We have to figure out how to tune this stuff appropriately. Now, there's best practices are meant to be broken, right? But realistically, what is the ideal approach for enterprise database systems, especially the categories that we would consider the biggest, the baddest, the weirdest, the most performance intense? It's a two-step approach. So how do we do this? Oleg?
Let us get started. Thank you, David. It's really my pleasure to be here on this webinar together with my old friend David Klee. And the real purpose, right, is to explain a bit how you can work to optimize your systems, right? And it's a common word that we have a best practices for performance tuning. However, is it just a simple thing, a simple set of recommendations that you can apply for each and every workload running on every type of storage, on every type of hypervisors? The answer is no, right? So we have a different workload types. And for each of that, we are working very hard to get the right set of recommendation for you, right? And as a result of our multi-year work with different customers, different partners, among of them Heraflux and David Klee, we created an Architecting Microsoft SQL Server on VMware vSphere best practice guide that we are maintaining and updating with all the relevant things that you need to know about SQL Server, describing how to go through compute resources, how to optimize your ESXi, and the overall vSphere environments. But let us break it down for you. So I will hand over to David to talk about compute resources.
Perfect. Okay, there we go. Okay, so at the bottom of the infrastructure stack, quite literally, there's tons of bells and whistles and TLAs and system components. Realistically, what do we have to worry about with all of the layers of tuning that we're doing? Very simple. 4 main food groups, to quote Michael Corey. We have a processor, we have memory, we have storage, we have network. All of these have to be lined up properly. Now, what is a hypervisor in general? It's simply a series of queues that allow your workload to get access to those compute resources. That's it. There's nothing more magic secret sauce to that. These are present for all of those compute resources. They are extremely hidden. The VMs don't know that they're virtual machines. They do not have direct access to the stuff, but they think they do. And these are not necessarily first in, first out queues. These queues can be prioritized by the hypervisor. So what we have to end up doing is optimizing to make sure that the number of resources in those queues is kept to a minimum, and that the time spent in the queues are kept to a minimum. If we can do this, we got bare metal performance. It's that simple. It's not always that simple, but it's that straightforward. So bottom line with all of this, tune from the bottom of the infrastructure stack. Every one of these layers has bottlenecks in queues, some bigger than others, some a lot smaller than others. But what do we need to do? We basically, if we tune from the top down, we're going to end up hitting some of these bottlenecks with a much larger hammer, and it's just simply going to backfire. So we're going to start at the bottom. We're going to start with enterprise storage. And I know what a lot of you are thinking. If you're DBAs out there, you're thinking, oh, storage, not very fun. Well, historically, this has been the bottleneck to performance. Realistically, the database architecture has assumed this for decades. That's why the database engines have such a large memory cache, because it's a storage read cache, basically. So bottom line, ask the questions. What are your databases actually doing with that underlying storage? You got a lot of data. Are you asking for all of it? Or are you asking for repetitive reads from this stuff? Are you asking for a ton of it, or just little hotspots here or there? And then, can your storage actually handle the demand of all of your SQL servers? And this is not an easy question. This is extremely random IO patterns, because if you have a ton of SQL servers, if you don't engineer this stuff properly, and if your underlying storage can't handle it, you may be funneling all this workload to one little spot on that storage array, and your storage array is just maxed out, and you end up with, to quote Keanu Reeves, whoa, that's not very fun. Well, not all storage arrays are created equal with this stuff. If you look at the speed over the years, you've got spindle drives, SATA-based solid state, SAS-based solid state, now NVMe. May spinning rest in pieces. It's not the most fun. I want you to be on as fast a platform as possible, because if you progress through the years, the random IOPS go up. The latency of this stuff goes way down. And when it comes to a database transaction, it's the latency that matters the most. It's not just the disk, though. It's a really common misnomer for a lot of folks out there. I can have the fastest storage on the planet, But if the path to get there and the act of figuring out where my data is actually at is super slow, it's kind of like you just bought an Italian supercar and it came with square tires. There's controllers inside all of these things. These are the pieces that understand where your data is at. They have interconnects to the outside world. There's the storage media itself. We have to make sure that we understand all of these pieces and how your storage actually lines up for all of those. So one easy way to go validate not the ongoing performance characteristics of your workload, but to validate the ceiling at where you're actually able to boost to is with a storage test. Now, this is not a SQL Server workload itself. However, there's this tool out there called Microsoft Disk Speed. It is the spiritual successor to the SQL I/O tool. We do have a no contact info required how-to guide out at hfxte.ch/disk speed. I want you to figure out what's your ongoing performance ceiling. How much can this thing actually deliver if you were to really push it? And then take whatever monitoring telemetry that you've got and line them up side by side. Am I asking everything that this thing can deliver? Or do I have a lot of extra overhead there? And how does this thing actually respond to the different workloads? So I've said it before, I'm going to stress it again. This is not directly a SQL Server workload because a database workload it's all over the place. You can have an 8K read, a 64K read, a 256K read, 1 meg read. It be all over the place and completely random. There's a big mix of read and write. Transaction logs right in a 60K segment. Really interesting patterns all over the place. But if you have this tool, you can simulate patterns for certain patterns in a given test. You can say X number of operations per thread, X number of worker threads, 80% read, 20% write, do random, do sequential. You can start and do block sizes, and you can start to go get a sense. How does the storage actually perform under varying degrees of workload types, intensities, scale, that sort of thing, and figure it out. Is storage the primary bottleneck? Now, we're going to go up a stack here to physical servers. I could spend the next 4 hours talking about just this one topic. There's so much in here. We're going to focus in on a couple of these. Processor is a big one because when you take a look at your CPUs themselves, pop up the task manager. There's a ton of information in here. CPU make and model, base speed, clock speed, number of cores, number of sockets, is hyper-threading enabled, cache amounts. Oh my! There's all kinds of stuff that you can do here. Cool. Oleg?
Thank you, David. Right, and that's really important for us to understand the way how on your physical server, your physical resources that you would be using to run your VMs and execute queries from your database, what is the layout, right? Because that is actually where the processing of your query is happening. So let us take a look at the main board and what we have in here, right? So the main components, it's a lot of them, right? And I'm not going to go into a lot of details of the architecture of your main board, right? It's a lot of trainings on top of it. However, for this specific exercise, what is important for us, on a modern server, we normally expecting to have multiple sockets. Why we are doing multiple sockets, right? Just because we need more compute power. And in addition to that, right, it's not only compute, it's not only sockets, right? They're very tied with the memory controllers, right? And memory controllers that what you're seeing residing just near of your CPU sockets. You might be asking, why not to place them like far away? Oh, because the distance matter. Right? It's not only really about to place the data. It's about how quickly I can access the data. That's why placing your CPU sockets and respective memory controllers all together helps a lot. And now we are coming to probably one of the topics that has been discussed for a long time and for a long period of time. That is about what we do with non-uniform memory access and how it can help me to boost performance of my virtualized workload. Before we dig into that, it's a very interesting topic. I can talk about it like for many hours, right? Let us get some important basic information covered. We need to distinguish between CPU NUMA architecture or uniform memory access. In a uniform memory access, we have just a single communication channel between all your CPU cores and your memory controller located on a node. And remember that from a way how this technology works, it's still just a serial access, right? So if your memory controller is now executing some calls from one particular CPU core, so it wouldn't be able to address other cores. So that will be a long queue, right? And as the increasing number of cores, this long queue is starting to affect performance because CPU are waiting to execute the call, are waiting to get the data from memory controller to be used for that particular call. So that would lead us to the next level architecture that was introduced by Intel in a later 2000, and that is what is called NUMA architecture. By non-uniform memory access, it's an idea that we are going to split memory between available sockets. In our example, and probably most of your physical server would be dual socket system, right? However, the same would apply for 4 sockets, the same would apply right now for AMD with some nuances for the way how AMD works with NUMA, right? And remember that Intel still was the one who introduced the NUMA technology. So for NUMA, we have a dedicated set of memory to one particular socket, and we have another set of memory dedicated to another socket. What does it mean for us, right? That is exactly where, if you will be looking at your server architecture, you will see a memory slot located in the near proximity of your socket and some slot being located in near proximity of the other socket. It's not only physical architecture of your motherboard. That is also the architecture that might, can, and could affect your performance. Because what is happening, if you can fit your workload to execute within that particular NUMA node, right, we will have a local access. However, if for some reason we need to traverse and access memory data located on a CPU socket 1, but the call is executed by a CPU core located physically on a socket 0, we need to traverse this communication path between sockets and then get to the data and get it back. So just to make it short, right? It's an additional latency, and latency means additional time. And time, from what David explained, means that we are staying longer in these queues that are introduced by virtual environment. David?
Yep. Yeah. Bottom line here. There we go. Bottom line, just like Oleg said, we have to make sure that this awareness of the CPUs and the sockets and this configuration around them, we have to make sure that the workload understands and sees this properly. Just like Oleg said, the locality absolutely is critical. Now, some systems are a little bit quicker than the other, but if we can keep the memory for a given workload at the same NUMA node as compute, we speed it up. Otherwise, you end up with a performance penalty, and that's not fun. Now, a super easy one to go fix, set the power savings to high performance, please. Go disable ACP IPNC state, set the power profile of the CPUs to high performance or enterprise, whatever they want to call it in your system. We're already green because we're virtualizing this stuff. Don't hinder your performance because, quite frankly, it slows your CPUs down. Your licensing is based on CPU. You don't need to slow this down. You need to get the most out of that licensing. So we're going to jump into your interconnects, specifically around storage. This is a real common challenge. The queue depths within your fiber adapters are generally set too low. They're set because they don't know what kind of storage you have. So they assume that you have, quite frankly, the most terrible storage on the planet. If you've got HPA or FCOE adapters, they're usually set too low. An example of this, Cisco UCS, the LUN queue depth inside the FC adapter policy for whichever platform you're on, VMware, Hyper-V, Windows, Linux, whatever, it's set to a value of 20. If you're on modern, true, good, solid storage, this is simply like, that Italian sports car with square tires, a 1-gallon gas tank, and only first gear. That's ridiculous. It's way too slow. Most of the others out there give you a value of either 32 or 64, which is arguably still too low. Set it, test it, validate it, but go higher. Usually 254, sometimes even higher, depending on the platform. You can end up with a lot better performance. The hypervisor layer gets more interesting. Essentially, we talked about the resources and the queues. So for the queues, what we end up with is a set of compute resources, CPU, memory, network, disk. You start slicing and dicing these things. Some of these things you can overcommit, like CPU, if you're careful. Other things you can't overcommit, like memory, or the amount of data that you write to your storage or your network adapters. You only get so much of these to slice and dice. The queues get really interesting with this stuff. Every single thing that the hypervisor does has queues associated to it. So whatever the VM is throwing in it, it's going to sit there. And if these things tend to start to stack up, everything can get impacted. And that's not where you want to be. So there are some really good best practices for this stuff. Take the hardware, set the power management to high performance. It's just like what we're doing with the physical machine, but we just want to make sure that this thing is not actively trying to slow us down. And this part doesn't take an outage, which is really helpful. Now there's another one. I always joke that certain companies, they have got terminology that makes it sound like they're the center of their own universe. It's kind of funny. There is a setting inside VMware specifically called disk.sched_num_rec outstanding, or DSNRO. What it really means is that a virtual machine and its dependent virtual disks are called a world. If one world and only one world exists on a given data store, which is VMware formatted LUN, the queue depth at that host to that data store is inherited from what the virtual machine is transmitting. So we're going to talk more about that as we work our way up the stack. But by default, it may not be very good. It's comprised of the number of queues and the queue depths associated with the disk controllers on the virtual machines. And that's just if one VM worth of data is on there. What if you have more than one, which is extremely common? If this happens, the queue depth to that data store is dropped to just 32. So think about it. We just cleaned up the queues underneath. We're now one layer higher, and we now have another artificial bottleneck. They do this because, again, they don't know what kind of storage you're connecting as well. Different company, different layer of bottlenecks. They assume the worst. They don't want to overwhelm older legacy storage, but you've got good storage now. So we can fix this, bump this up. Test it, of course, but if you're on flash hybrid or all flash, or especially NVMe, go crank these values up, because it really does matter. And there's a document right here that will tell you how. Now, let's start talking about the virtual machine. And Oleg?
Okay, so now we are talking VMs. And VM is in a virtual environment, right? That is a object, or even, I don't now use the word container because it has a lot of different meaning, right? But it's still, a virtual machine is the way where you execute your workload, where you execute operating system and run your database workload. So configuring properly your VM is the next level of tuning that should be performed on a virtualized platform once you have done everything right on the ESXi side. And VM itself, right, it's a representation of physical hardware. And believe me or not, right, guest OS is still running inside of VM, right? Guest OS nowadays still treats that as they would be running on a physical hardware. How we are dealing with that stuff? To help with that, we introduced what we call virtual hardware version, or in a modern version of vSphere, we now using is the terminology virtual hardware compatibility. Virtual hardware compatibility is really overseen a lot in terms of what that can provide for us, right? And how it can be helpful, sometimes unhelpful, right? So virtual hardware compatibility, you can compare to a virtual motherboard for your VM, right? And basically every time when you're changing virtual hardware compatibility, that has a close effect when you're changing a motherboard in your server, right? And virtual hardware affects not only what you cannot do inside of VM. So for example, when we are saying that you now can run up to 128 vCPU inside of your VM, yeah, you can do that. However, it would require version 50, right? But it's not only that. If, for example, we are saying how many virtual CPU, how many virtual disk control, how many virtual disk, virtual memory you can assign to a VM, that is all being controlled by virtual hardware. And also an additional thing, right? For example, we introduce support for Intel Skylake starting at virtual hardware 40. What does it mean? That if your VM is still running on virtual hardware 8, even on a ESXi 7.0, guest OS inside would not be able to take any advantages of advanced instruction inside of Skylake processor, right? They would be hidden because virtual hardware is not exposing them. So recommendation is definitely test before you upgrade it. And remember that upgrade is just a one way. It's no official way to go back if you don't have a backup on a VM level object. And always make sure that you have a reliable backup, and not only backups that you know that exist, but also the backups that you can restore. So, and definitely upgrade your virtual hardware once you have all hosts in the cluster running on the same version of ESXi. Remember, once you bump your hardware, you wouldn't be able to go to the previous version of your ESXi that would be required. David?
Okay. Just like Oleg said, the hardware architecture for this stuff is absolutely fascinating. Again, I could spend the rest of the week on this stuff and probably part of next week as well. We have to figure out, what do we need? Just like I mentioned before, we need to minimize the amount of activity in these queues to only what we need. Tiny, small amount of headroom in there, but realistically, how many of these compute resources do your workloads actually need? And I stress need, not what do you want, not what do your third-party vendors say you have to have, because most of the time they don't get it right. You have to go through a right-sizing assessment, especially around CPUs. Allocate what you need with a reasonable amount of headroom in there. By doing this, you're going to reduce the amount of objects that are going to go through the schedulers, and there's a high likelihood that you're going to reduce the scheduling time stuck in these queues. When you do this, you make it more efficient. Making it more efficient improves performance. So you got to figure out, what sort of telemetry do you actually have? What do you actually need? And there's this whole series of tasks that we could talk about with that, with business critical time versus weekend time versus nights. Are things running time sensitive? Do we have more time than allowed, even though it's running hot? Those sort of things. You can always expand this thing down the road. So on this particular machine, 64 core SQL Server. Take a look at this. One is active, the rest are really quiet. Do you need all 64? No. This thing would work just fine on 8 cores, and just at 13 grand per 2 cores of enterprise licensing a SQL Server. Think about how many toys that can buy.
Okay, I probably know what we will be talking here about, right? So now let us cover CPU scattering. And as David mentioned, right, it's really important to do the right sizing. And why it's important, let us take a look at a way how we scatter CPU resources. And I still believe that ESXi CPU scatter is probably the best scatter in the world that was ever involved in the virtualized environment, right? But understanding how it works helps you to understand how to make a workload to be of a benefit of it, right? So we definitely have an actual execution, right? So actual execution time, it's absolutely comparable between physical and virtual, right? It's the time that is required to take the data, do the operation with the data, and execute these threads, right? However, as we are running on a virtualization system, right, it's also an additional things, right? So first of all, the CPU scattering cost. What does it mean? That the request from a VM should go to the ESXi. ESXi CPU scatter would pick it up, and ESXi would know how to spread it between different resources. And if you have multiple resources in here, then we will have what is called ready queue. Ready queue means that VM is okay to execute. It's the time that we'll spend in a ready queue, right? That is why we have that much of request and that low CPU cores to be executed, that CPU thread from a VM would need to wait. How long does it need to wait? That depends on how fast we are scheduling them, how many CPU we have, and how many CPU VM has. And that is what is reflected in a ready time. We can measure ready time per core or per VM, but percentage of a ready time, that is exactly your trade-off of running virtual, right? That is a delay of your CPU threads when you're executing them from a VM on a physical hardware. That is a key metric for you to look at. And the goal is to make your ready time as low as possible, right? If you get your ready time close to 0, that would be exactly the same as you're running on physical. If your ready time is 25%, then you're basically running 4x worse compared to a physical server. So keep an eye on it. That is a very important counter. And now understanding how that works, right, will help you to better fit your workload. And by the way, if you have too many CPUs, that is what David talked about, right, that would affect the whole queue, right? Because even if right now we are not necessarily looking at it, right, but it's still some delay when we need to check all the CPUs assigned to this VM and see, oh, do we have something to execute on, right? So please be aware. And now let me take over back to David.
Excellent. Yeah, the CPU scheduling is one of those areas that I could spend a lifetime studying this. Quite frankly, when storage becomes less of a primary bottleneck to database performance, we end up with this cycle here starting to become one of the bigger bottlenecks. And it's magnified by bad code, bad database design, not having the data spread out appropriately. So we're going to talk about distribution of CPU. You get the ability in any of the hypervisors out there to set the number of cores and then align them with the physical NUMA topology. But you got to understand the physical NUMA topology first before you can even guess as to what to do there. So you got to align this thing properly. Now, vSphere 6.5 and vHardware version 13 and above automatically manage this for you. It doesn't tell you on the front end, but it does automatically manage this. Be warned, if you need a non-standard NUMA architecture, or if you have a mixed hardware topology in your vSphere cluster, you need to be very careful of this because it may not always do exactly what you might expect. Now, the rules of thumb with this, best practices, all the usual terms that are meant to be broken. Take the right-sized amount of CPUs that you've got. Now, let's just say this physical server is a 2-socket by 12-core machine, 512 gigs of RAM total. So each NUMA node, 12 cores, 256 gigs of RAM. If the vCPU count fits inside one physical socket's worth of physical cores, I generally ignore hyperthreading, then build the VM for one socket with that number of cores. Make sure the memory fits as well. Now, if the VM does not fit inside one, cut it in half, subdivide it, see if that lines up. If it still won't fit, go to 3 sockets, 4 sockets. This is actually what vSphere is doing automatically under the hood. But be warned, make sure it gets it right. Part of the reason I always say be careful with this is that at the time of this recording, it doesn't look at the amount of memory in there. So if, let's say, the cores fit in one socket, but the memory does not, you now have remote NUMA memory lookups going on under the hood. You can end up with an imbalance there. So you may need to manually override and force this kind of architecture in there. Now, don't open the task manager. It does what you told, it reads what you told VMware to do. It may not be what's actually presented, but inside the database engine, you can verify this really easily. If you right-click on the SQL Server instance, hit Properties, go to Processors, you'll see all. Expand that out, you'll see your NUMA nodes. Expand that out, and you'll see your individual cores under there. If you want to go a little more old school, kind of like what I love to do, simply hit Select Stuff from sys.dmos nodes. And now you have your NUMA node ID with your online scheduler count and your CPU count. If those don't line up, something is definitely not right because SQL Server can't use all of those existing cores. Watch for nodes offline. Watch for the different scheduler count. It could be because NUMA is imbalanced. It could be because you've got more cores than what Standard Edition will allow you to do. There's a lot of different pieces in here, and you just simply have to verify. Trust, but verify. Oleg?
So we talked about CPU resources and the way how you can assign it, right? Now let us take a look at the storage, right? It's not only physical storage that you have, it's not only your great sense storage that is running your all the I/O for you. EVM itself also should have an interface to be able to send I/O to ESXi's, and ESXi will take care of them, right? What is that interface? That interface, we are calling it virtual SCSI control. And it's a one addition that I will be also talking about, but let us just talk old school. It's a vSCSI controller. So vSCSI controller, that is the way how we attaching disk, and that is how we emulating for EVM. It's like if for guest OS, it's like running on a physical server that will be able to see all this great SCSI controller, and that is where they would be sending its all I/O out. So now an interesting question, right? So what would happen if I have like 8 HBA on my ESXi? I will have 32 controllers on my physical storage, but just one single SCSI controller inside of my VM. You're absolutely correct. That is where your I/O all would be queued for a long time. We do support 4 SCSI controller per VM, and let us take a look at the controller types, right? Because, you know, it's also matter. We support different controls type. The default one for Windows SAS will be LSI logic SAS. And we will talk about it in a minute, why it's important, right? But we do have another type of it, which is LSI logic parallel, really coming from the Linux word. Paravirtual or VMware Paravirtual or PV-SCSI control, it's a different name for it. However, that is the one that was introduced exactly for virtualized infrastructure. And that is the one that would get you best performance. And as I promised, in addition to that, we're also adding a new type in your ability to connect your storage using NVMe virtualized controller. It's not exposed as a SCSI controller because it's an NVMe controller, right? But it's also available for your workload, and we'll talk about it in a minute. So why we still have LSI logic SAS? It's 20 years old, right? It's a great thing if you go back to beginning of 2000, right? The real reason for that is a compatibility, because Windows OS still has default driver incorporated into installation ISO for LSI SAS, and it's not available for VMware Paravirtual SCSI controller, right? So that is why we still support LSI SAS. That is still a default controller for Windows operating system, but it's as very good written on this slide, it's present for compatibility, not for performance, right? And do not attach the maximum amount of your virtual disk to just a single LSI SAS adapter. It wouldn't help you, right? For that one, we have VMware Paravirtual SCSI controller. VMware Paravirtual SCSI controller were engineered for performance, right? That would not only give you a quicker way to send your I/O. It's also at a lower CPU utilization. So it's a really win-win, right? And it was introduced a while ago with ESXi 4.1, right? And we did a lot of investigation at that time, right? And believe me, it's really lower your CPU utilization on a higher I/O bundle. And in addition to that, we have a way to manage queue depth that is 64 by default on a version 6.7, and starting with 6.7 update 1, we are now defaulting to 254 for all new installation and the new version of VMware tools, right? So be aware of it, just because we want to maximize amount of parallel I/O that we want to send from guest OS back to ESXi and back to the disk. And now it's an important, right? We do support a maximum of 4 SCSI controller per VM. That might or might not be enough for you, right? Depending on the number of disks, depending on how many disks you want to attach to each of them, which is 64 being still maximum amount of VMDK per SCSI controllers that we support. What you can do if you really want to have maximum amount of disks spread between multiple SCSI controller, you can do up to 4 PV-SCSI and 4 NVMe. NVMe is a new SCSI controller, is a new controller type. sorry, it's not a SCSI one, right? We still think that on our performance benchmarking that VMware Paravirtual would give you better CPU to IO ratio when you're using VMware Paravirtual. So stay with VMware Paravirtual at the moment, but you still can get a try with NVMe and it might fit to your workload. Do the test, establish the baseline, do the test again.
Perfect. Now, here's the hard part. You've got all the controllers. You've got the option for a bunch of virtual disks. What do you do with your databases? Well, this goes back to what sort of operational telemetry do you have? You've got tons of information in the SQL Server DMVs. You've got Windows layer. You have whatever monitoring tools you want. Now we have to figure out, how do we distribute this data? So let's just say you got 4 PV-SCSI controllers. Well, you may have a bunch of virtual disks. How do you spread this stuff around? It's up to you. It's very up to your workload. I do want you to standardize your deployments the best that you can, but this is where it matters, where if your underlying storage is world-class and your interconnects are stellar and fully optimized, you've still got all the queues at the hypervisor. You've still got all the queues in the operating system, and then you've got queues inside the database workload. So as a set of base standards, spread these things around. 1 or more drives for database data on its own controller, another drive for logs on its own controller, the TempDB database. If your workload stomps on that, give it its own controller. You may have some other drives in there. Use your workload telemetry to figure out where to best actually attach these things. If you don't have anything fancy, you do. You have Windows Perfmon. You can collect this 24/7. It's completely free. It's built in. We love to collect it as a 30-second granularity. We do have a setup document out here at our website. Again, no contact info required, but this gives you the ability to actually see exactly what this thing is doing. Now, if the controllers or DSNRO are starting to hold you back, VMware's got some of the best telemetry out there for this. There is a counter. I love this one. It's called the average number of outstanding read or write requests. This is quite literally IO operations stuck in these queues trying to get through. So if you pick your virtual machine, hit performance, advanced, go to counter option, or go to metric options, go to virtual disks, select the top 2, average number of outstanding read and write requests. Make sure you have all of your disks selected in the bottom right, hit OK. And what you end up with is a chart that looks like this. Most of the time, it's not that big of a deal, but if these queues are stacked up, you're going to see really high elevations there. Now, how high can it go? There's actually an internal, pretty undocumented cap at a value of 1280 per drive. Be careful, monitor this stuff. If you don't have your vSphere statistics collection level set too high, this is only real time. Be careful because this stuff matters. Look for hotspots on these drives. And as a basic standard, you can turn around and start to standardize and make this stuff work for you. Now, part of this could be because you may have a misaligned block size. The database environment has some pretty large blocks out there. The standards, Microsoft has dictated this for forever, 64K NTFS allocation unit. I always say if you're on hyperconverged, test it for an 8K, just ignore the marketing material, test it for yourself. I find that on hyperconverged, 4 or 8K generally do better, but for everything else, 64K should be just fine. But again, test it. Also, leverage the large NTFS file record segments called the FRS flag. By default, it's a 1K block for metadata management for NTFS. This makes it a 4K block, so 4 times less pointers for your workloads to have to go manage. Not too shabby. Now, move forward a little bit. Let's bump up to the CPUs. We spent all this time on vNUMA and physical NUMA. Let's make sure your database workload is actually able to take advantage of that. There's a setting in the database engine called the max degree of parallelism. And if a query goes parallel, this is up to the amount of CPUs that this thing is going to try to parallelize against. By default, it does everything, or if you're on 2017 or above, it's a number of cores, or 8, whichever is lower. My rule of thumb for this, if it's a single NUMA node, Set this to the total number of cores, or 8, whichever is lower, and then validate to make sure your workload is not actually going to just crush everything and that you have to reduce this to, leave headroom in there for everybody else. If you have multiple NUMA nodes, set this to the number of cores in one NUMA node, or 8, whichever is lower. Keep that workload isolated to that one NUMA node, so the memory lookups are going to be local. Now, if it's physical and if hyperthreading is enabled, go from 8 to 16. I generally try not to worry about hyperthreaded in there. One other thing to think about is large memory pages. Again, I'm trying to be efficient. The Windows layer by default manages memory in a 4 kilobyte segment. Enabling log pages in memory, and on Enterprise Edition of SQL Server, setting trace flag 834 allows you to take that 4K footprint and make it a 2 meg block. It's got to use Enterprise Edition. It's not the most fun. It doesn't work with column store indexes. Microsoft is aware of this. Who knows what they're going to do with it. But bottom line, this is where you can turn around and make a pretty substantial performance gain. In virtual environments, we see anywhere from a 17 to a 40% performance gain just by making your memory footprint more efficient. Now, that gives us our workload itself, the basic standards that you can apply to everything. But now, when we go and we have these big, severe workloads, you can't just apply basic performance tuning techniques. We now have to get to the point where this is workload specific. And this is where things get even more interesting, because we've got our standards. Now we have to go beyond that. All these things can matter. It could be that we've got reporting and decision support that's just stomping on a relational system. It could be the database structure worked great with 1 million records, but it doesn't work well with 1 billion records. It could be bad table design, indexing, bad queries, commands, you name it. This is where things really start to matter. As it relates to storage, when we start getting a ton of SQL Server activity into a given database, the default is 1 data file and 1 log file. You can actually go start to see where we're at with this stuff. There is a metric in there called disk stall. It's SQL Server's equivalent to storage latency. If we start to see read latency as SQL Server sees it, but we don't see it in the underlying operating system or the hypervisor or on the SAN, that's metadata pressure inside the database engine. More file groups, more data files. And now we need more queues for all of this. So more virtual disks, more controllers, maybe database partitioning, maybe more SAN LUNs, maybe more SAN controllers with more LUNs to spread out this workload and reduce all of these pinch points underneath and let this database engine run as fast as humanly possible. You can do this. We do have a free script out there, hfxte.ch/disk stall will give you a script that will ongoing collect these metrics and will help you see the disk stall rates by database data in log file. Compare it to perfmon, compare it to VROPS, compare it to the VMware telemetry with virtual disk and data store, and then compare it to your SAN. And what you may find might probably surprise you. The database engine can start to trip up on itself. This is why we have more than 1 data file for TempDB. Do it for your user databases. Now, if you're in this position and you have to scale this stuff out and you got 1 big old database file right now, and we hit a bunch of these. We had one, there's a 16 terabyte cap on there, and they had a lot of them. Go out to my home blog site here at davidklee.net. There's a post I recently put out there about how to take these data files and spread them out. Now, this is assuming it's 1 file group, but you can do the same thing for multiple file groups, non-clustered indexes, commonly joined tables, but there's a full thing out there that shows you how to add more data files, more drives, more controllers, more LUNs, etc. And then live, you can actually shrink the MDF and have it drain into the NDFs until they're equal. Shrink the MDF appropriately, and now you've got a more parallel and balanced system. It's pretty fun. Now, we're going to hit a demo here related to the DVD stored database benchmark. And I want to show you, here is a plain Jane install of a virtual machine with literally a click-through install of SQL Server. This is what I see so many times. It's not even funny. You end up with just, it works, but it doesn't work well. The second one that we see is going to be, if we follow the SQL Server Best Practices Guide for VMware vSphere to the letter, no code changes at all. This is where we're going to end up. The third example is going to be, again, the exact same workload, but the database structure has now been modified. More data files, same number of file groups, but more files per file group. And we're going to be better distributed amongst the underlying storage. And we're going to see exactly how this thing lines up. Okay, to demonstrate the difference between multiple SQL servers and their configurations related to infrastructure, storage performance, things like that, we can either reproduce a production workload in one of our existing environments, which is a lot harder than it sounds, or we can use a synthetic workload generator. Now, there's two that we like. One is HammerDB, the other is DVD Store. Now, these are not perfect tools, but they are a good way to produce a reproducible workload on a given SQL server and try to look at the differences between the exact same database that's been restored in different places before and after you make a change. So if you go out to github.com/dvdstore/ds3, that is the third version of the DVD Store benchmarking tool that we are using here. It's cross-platform. We're using it for SQL Server. Just download the code, extract the zip file, follow the directions. We actually do have a guide out at our commercial website, heraflux.com, that will give you a walkthrough of how to generate the data set, load it up, and run the test. It's pretty straightforward. What I love to do is to create either a PowerShell file or a batch file. We're going to run the SQL Server driver. It's a workload driver. And essentially, let me zoom in here so you can see that. So essentially, you can see we have our target. It's going to be the destination SQL Server. We have the number of threads, 16. This time, we're going to do a 60-minute runtime, just so we can let this run and warm up. Ramp rate of 1 means we're just going to keep this pretty quiet. Target database size, about 250 gigs. Warm-up time, 0. Think time 0, meaning hit this thing about as hard as we possibly can. Percent new customers, 20%. Number of searches per order is 2. Search batch size, 2. Number of line items per order, 5. Detailed view, yes. And then what I'm going to do is set an output file name so that we can track the results compared to the different tests here. You'll notice I have test SQL Tune 1, 2, and 3. I have 3 SQL servers on the back end. The first is going to be a SQL server that is just, no kidding, click through on a virtual machine perspective and then click through on a SQL Server perspective. Unfortunately, out in the real world, this is what I see more times than not, than I really care to admit. The double-edged sword with SQL Server is that it will work in that architecture. However, it may just not be optimal. The second SQL Server here is, again, exact same database, exact same workload parameters, but is tuned for SQL Server on VMware best practices per the SQL Server best practices guide from VMware Corporate. Basically used it as a checklist, built out the second machine. The third is what happens when you apply all the best practices and then take a really good look at the workload between them all. Now we need to figure out more data files, more file groups. In this case, they have a bunch of file groups already, so we simply added more data files per file group. We tuned the cost threshold of parallelism and max degree of parallelism, added a couple of trace flags for normal read-ahead workloads and statistics and normal stuff that we do for these big enterprise workloads. Now, if I minimize this, you'll see that the test is already running here. The thing that we care about here is this value right here as it flashes by, OPM equals. That's the benchmarking result here. It's orders placed per minute, or OPM. So if you see the top on here, that is our original SQL Server number 1. That's basically just a plain Jane installation. So right now we're hovering about 8701 orders per minute. If we take a look at our second SQL Server on here, orders per minute, we are almost double that. 16,188 at the last checkpoint here. That is almost double as fast just simply through going through the SQL Server on VMware Best Practices Guide. Now, that gets us to the 80% mark. Let's go to 100%. This particular workload benefits from having more than one file per file group. We have these things distributed amongst multiple paravirtual SCSI controllers. We have this stuff tuned properly all the way through the stack. Take a look at this. Instead of, 8,700, then 16,190 something, now we're at 22,000. So you can see it's incremental gains at this point, but this is how you get the biggest bang for the buck out of the workload that's out there. Now, if we take a look at our SQL Server configuration, there's really nothing that fancy in here. And there's some warnings on here for CPU usage, but that's normal because we're hitting these things pretty hard. If you notice, 16 cores, 96 gigs of RAM. With this being the first one, our SQL Server workload is all on this drive right here, 500 gigs. But you notice one LSI Logic SAS controller, it's pretty plain Jane. There's nothing fancy about it. When we go and look at the second one out here, now we've got the SQL Server on VMware Best Practices Guide. We've got VMware Paravirtual SCSI controller. Same thing, 16 CPUs, 96 gigs of RAM. Nothing fancy. 5 hard drives though. That's one of the differentiators. We've got the data on one drive, we've got logs on another, we've got temp to be on another, and we got backups for our transaction log local backups on another one. If we take a look at the third one, it's obvious we're hitting this one pretty hard because we've got a CPU warning on there. 4 Paravirtual SCSI controllers. Now, 13 total drives. We've got our NUMA lined up properly, but in this case, we've got our databases distributed amongst a lot of little drives distributed properly across the individual controllers. So SCSI ID, 1, 2, 1, 1, 0, 3, 3, 0, et cetera, et cetera, et cetera. We've now got this thing distributed to have the best possible means to get through the hypervisor, CPU, and resource queue schedulers, especially storage here. Now, at the end of all of this, this is quite literally what matters. You can see we have basically plateaued for all of these tests, about 8,700 for the default, about 16,000 for the proper one, and about 22,000 for the one that's properly tuned for the workload. Again, the workload generator and the database is the same. The only thing that we did was scale out the database workload to more controllers. That's it. So it's pretty darn impressive. Now, if the storage underneath is already stellar, these kind of changes get magnified with the actual performance of the SQL Server simply because this stuff matters. This stuff matters a lot, and you can see very easily. Now, don't take my word for it. Go test it in your own environment. DVD Store and HammerDB are both completely free. We have how-tos out at heraflux.com. Go check it out. Do this for yourself. Go verify these changes. Now, we've gone through the infrastructure stack. We know that our storage is no longer the primary bottleneck to performance. Our interconnects to get there aren't holding us back. The physical server is tuned and the workload is aligned. The hypervisor queues are kept to a minimum. Everything looks great. And then we've tuned our database workloads. This is how you tune this. You standardize, then you tune for the workload, and you end up maximizing this massive investment in SQL Server licensing. The business benefits, people can be more productive. The demand on the system is less, so you compile more on there and you end up with performance gains. Life is good. Now, just with everything that we said here, question everything we all say. Please always test all of this stuff. Every workload is different, but that's part of the fun. You can now tailor this. If you have bottlenecks in your environment that I didn't talk about, you'll be able to spot them and see them, and you can go tune this. If you're interested in learning more about how to do this, specifically on the VMware platform, we recently released an 8.5-hour on-demand boot camp for how to go through the environment, bottom to top, and clean up all of these queues. We just scratched the surface with what you can get into with VMware and Windows and SQL Server and Linux. So go check it out. For you, there's a 50% promo code. If you go to SQLibrium.com, enter Pavilion in the checkout process, you'll get a 50% discount. If you have any questions with that, do not hesitate to let me know.